Okay, so hello everyone. Today I'll be having a discussion on the week 9 lecture series that you have attended. I'll try to clear some of the concepts that have been discussed in week 9, along with some of the relevant questions related to those questions, some numericals, some concept-based questions uh, based on the knowledge that you have gained by attending the lectures of week 9. And in that way, I think you'll be able to better answer your assignment in week 9. And so we'll get started very shortly. Just waiting for a couple or 2 minutes. We'll try solving some of the questions, and in case uh, you are finding difficulty with some other questions or some concepts, you can uh, mail to me. Okay, we'll very shortly share the my slide pertaining to the questions of this week. Just excuse me for 2 minutes. Okay, sorry for the interruption. So yeah, starting shortly. Okay, so let's get started for this week. Hmm, okay, the slides are visible. Okay, yeah, they're visible. I'll enter the slide. Okay, so okay, welcome once again to week 9 doubt clearing and problem solving session. So I am Akash Jyoti Pathak. I am your course assistant for this NMR spectroscopy for chemists and biologists. I'm a PhD scholar in IIT Bombay, and I am uh, the course instructor. On behalf of the course instructor for this course, Professor Ashutosh Kumar and Professor Husu, I'll be helping you with this sessions lecture classes. Uh, okay. Okay. Hmm. So we'll start. Okay. Ah, so this is the first question of today's session. So the question is an RF pulse applied along the x-axis causes. What effect does an RF pulse that has been applied along the x-axis happens to have on the bulk magnetization? Okay, that is to have on the bulk magnetization of the nuclear spins. So the RF pulse has been applied along the x-axis. So the general assumption that we'll have to consider is that the nuclear spins, all the nuclear spins are in their equilibrium state. Okay, so the bulk magnetization overall is in the z-axis, right? And at at such a state, you are applying an RF pulse along the x-axis. And the options are magnetization. First option is magnetization to align along the x-axis. Second is rotation of the magnetization in the xz plane. Third option is rotation of the magnetization in the yz plane. And fourth is rotation of the magnetization in the xy plane. Right. So for this question, you'll have to have the knowledge of right hand thumb rule. So right hand thumb rule, what does it say? So if you are using your right hand thumb rule, then your curved fingers will give the direction of the flip of the magnetization, okay, upon the application of the RF pulse. And your thumb, right hand thumb, that will be directed along the direction in which the RF pulse is applied. So once you are orienting your right hand along in that manner, so that your thumb is in the direction of the RF pulse that is applied, and uh, your fingers, your rest of your fingers are along the equilibrium magnetization, bulk magnetization. You are placing it along your bulk magnetization, and then you are, and this is your thumb. So right hand thumb, you are orienting it along the x-axis. And now when you'll be curling your other fingers apart from the thumb, the direction in which it curls, okay, the direction in which it curls, that will tell you the plane in which your bulk magnetization will tip off, right? So say, so we will be following the Cartesian coordinates of x, y, and z, right? So okay, so this is x, this is your y, and this is the z, right? This so now as per the question, the RF pulse has been applied along the x-axis, right? So x-axis, as per my diagram that I have drawn in the here, as a, what the diagram that I've drawn here, the x direction is point is towards my face, okay, towards coming out from the plane of my screen and facing towards me. So this is my x-axis. Okay, and the bulk magnetization, your rest of the fingers should be aligned along the bulk magnetization at the equilibrium state. In the equilibrium state. So this is my x-axis, and which is pointing towards my face, and this is the z-axis along which the bulk magnetization is aligned. Now, if I'm curling now, how will I find that this torque, what torque, the application of this torque, what effect will it have on the bulk magnetization? For that, I'll have to curl my fingers. And when I'm curling my fingers, I'm finding that from the z-axis, it is moving to the, it is getting oriented towards the xy plane. Okay, xy plane. So the an RF pulse applied along the x-axis causes the rotation of the magnetization or the bulk magnetization in the xy xy plane. So this is your xy plane. In that plane, your uh, bulk magnetization will get flipped upon the application of the RF pulse in the x direction, right? Uh, X and YZ. Hmm, a minute. I think rotation of the RF pulse along the, I think there is some mistake. Rotation in the into the 1 minute. I'll just check a bit. 1 minute. Okay. So I'll check once 1 minute. Uh, so 2 seconds. 1 minute. Okay. So I just cross check. Hmm, I think there is some mistake. 1 minute. X, Y, X. It is applied along the x-axis. Then this is RF pulse. Sorry. Pulse. RF pulse is applied along the x-axis, and this is my z-axis. That axis along which the my bulk magnetization is oriented. So it will be in the XY plane. Okay. So there is some mistake here. Huh. So let's get right. Okay. Hmm. Okay. So okay. Hmm. Huh. The RF pulse is applied. And this, so if my bulk magnetization is along the z-axis, then application of the RF pulse along the x-axis, that will tip off my bulk magnetization, tip of the bulk magnetization from the z-axis to the xy plane. Okay, so this is the xy plane. So not what is the okay. So what is the answer here given? Option C. But this is actually wrong. Okay. So the correct answer not YZ plane, not YZ. YZ plane is YZ plane is your this plane, right? 1 minute. I'll just YZ plane is this plane. This is the plane. Okay. But my bulk magnetization B naught or M naught is along the Z axis, and I am applying the RF pulse along this axis. So my bulk magnetization will tip off from the Z axis to the actually the negative y axis. So my bulk magnetization, I can say that it will be in the xy, in the xy plane, xy plane. So this is the option D is the correct answer. Okay. So okay. So this is the effect of the, so this application of the RF pulse, what does it cause? It causes the application of a torque. It is actually applying. So, but please ignore the option. This answer is given wrong. This is not option C. It will be option D. The explanation is also therefore a bit misleading in this case. But the main thing that you have to understand is the right hand thumb rule that you'll have to use to answer such type of questions. And because of the RF pulse application of the external RF pulse, what does it do? This RF pulse is applied. So later on. Okay. So this is the, so now this is what you'll have to remember, right hand thumb rule. I think you have understood the right hand thumb rule that I explained just few minutes back. Ah, so this is wrong. This will be XY plane. Okay. Or XY plane. So let's move on to the next question. Okay. So the next question is based on the spin echo concept. Okay, which is also related to a kind of experiment which is known as CPMG experiment. Okay. So a spin echo arises because of these are the four options that are given. The first option is refocusing of chemical shifts, refocusing of coupling constants, inhomogeneity in the main field, or is it inaccuracy in RF pulses? Okay. Just I'll give you a couple of 2 minutes, 2 to 3 minutes to think on this, and I'll then explain. And there is also this reference diagram for you to understand. If you have gone through the lectures in this week 9 and week 8, actually in week 8, then this answering this question should be a cakewalk for you. And with the reference diagram and illustration shown here, it should be more easy. So just to refresh your memory on the spinnaker concept, this is the reference diagram. I want that you think on this for just a minute or two, and then I'll be explaining it. Okay, so we'll try to understand and solve this question. So the answer is because of refocusing of the coupling constants, right? Because of refocusing of the coupling constant, option B. refocusing of chemical shifts. Uh, Refocusing of, in case of inept, we'll get that refocusing of coupling constants. But in case of spinico, the option is option A, right? Refocusing of chemical shifts, right? So this is the chemical shifts. That the thing, the concept is something that has been discussed in the first week, right? So that is the basis of NMR spectroscopy. I think you remember this. Chemical shift. Chemical shift is the influence that each of the nuclei experiences because of the presence of other nuclei in its surrounding, right? Because of the different kinds of bonds and different kinds of atoms that are there in the vicinity, their electronegativity and attractive forces, we get different chemical shifts for uh, each of the nuclei, each of the maybe it is whether you are looking for proton nuclei, then also the proton nuclei because of its association, because of its bonding patterns with different carbon atoms or different electronegative atoms, you will see that the chemical shift of the hydrogen, yeah, or the proton is different from the other protons. Okay, so now let's try to understand what is this spin echo experiment. Okay, so this spin echo experiment starts with applying a pulse. Okay, applying a pulse. What is this pulse? The pulse is also known as the 90-degree pulse. Okay, the 90-degree pulse. 90-degree, to be precise, it is also known as the 90-degree hard pulse. Okay, so when your all the nuclear spins are in their equilibrium state. Okay, in their equilibrium state. So this is the situation when all the nuclear spins are in their equilibrium state or the bulk magnetization. This red colored vector that is pointing along the plus z axis, that represents what? That is the bulk magnetization vector. So at equilibrium state, where is this bulk magnetization oriented? In which direction is this bulk magnetization oriented? It is oriented in the plus z axis, right? It is pointing towards the along the plus z axis. Now this bulk magnetization is what? That is the ensemble of all the nuclear spins at their equilibrium state. Okay, equilibrium state means when the external RF pulse has been removed and all the nuclear spins are influenced by the external magnetic field that is existing in the NMR spectroscopy instrument. Okay, so because of that, the nuclear spins will orient themselves along the plus z axis, and the ensemble of all the nuclear spins will have bulk magnetization that will be oriented in the plus z axis. Okay, now at such a situation, what I'm doing, I am applying a pulse. Okay, I'm applying the pulse in such a way. Why is this called 90-degree pulse? Because this pulse will cause the 90-degree flip of the bulk magnetization. Okay, so if it is in the z axis, what will happen? From plus z axis, it will get flipped to uh, plus x axis. Okay, so I'll be applying the RF pulse in that manner only, such that that RF pulse, which will cause the bulk magnetization to change its orientation from the plus z to plus x, okay, or plus y, okay, the any direction that is perpendicular to my equilibrium or bulk magnetization. Okay, equilibrium bulk magnetization, yeah, that is known as a 90-degree pulse. So if I'm trying to tip off my bulk magnetization from the plus z axis to my plus x axis. Okay, or say if this is y, sorry, if this is x, this is y, and say this is my z. So my bulk magnetization was in this initially, and what happened from this plus z, it tipped off to plus y. Okay, so now in which direction did I apply the RF pulse? So based on the previous concept in my previous question that I discussed, when I answered that, for that what I'll have to do, I'll have to uh, apply my RF pulse in the negative x direction, right? if I'm applying my pulse in the RF pulse in the negative X direction, what will happen? You will have to orient your right hand thumb rule along the application, along the direction in which you will be applying your external RF pulse. So it is in the negative X. So this will be it. This will be the direction. And my equilibrium bulk magnetization is in the plus Z axis. So application of the RF pulse in this negative X direction will tip off my bulk magnetization from the plus Z axis to this plus Y axis. So I have applied the RF pulse in that manner. So that the bulk magnet tips off from plus Z to plus Y axis by applying what? A 90-degree pulse. Okay, so this is it, 90-degree pulse. And after that, what I'm doing, upon application of this 90-degree pulse, what happened? 1 minute. Sorry, I'll not this. I'll keep it. This will help you understand it better. So I'll keep this line. Okay, so this is what? This is A. Your A figure. It represents the state when you have when the entire system, okay, your sample solution, the nuclei, they are in the equilibrium state. So at the equilibrium state, the bulk magnetization is in the, so this is what the red dot is representing. It is in the orientation of plus Z axis. Okay, it is oriented along the plus Z axis. And now I am applying the 90-degree pulse. Okay, so this is your B diagram. So I'm done with the application of the 90-degree pulse. So as soon as you have irradiated the sample with a 90-degree pulse, what will happen? The bulk magnetization will tip off from plus Z to plus Y axis, right? So this is what the figure is representing at this point, okay, at the end of the application of the 90-degree pulse. So I will ensure my 90-degree pulse to be for that much duration, such that all my nuclear spins gets tipped off from plus Z to plus Y direction. Okay, so this duration I'll have to ensure. Okay, so there is a program in your the NMR is NMR software. Okay, there you can easily achieve this. Okay, by giving a command. So that will ensure that all the nuclear spins have oriented themselves from plus Z to plus Y axis. And then again, what I will do, I will give some delay. Okay, what is this delay? This delay I'll be giving it for a time say t. Okay, for a time t, I'll be giving a delay. What is this delay? This is the delay. Delay means what? What is this delay referring to? This delay means that I have stopped the RF pulse. Okay, so after here at this position, I have stopped my external RF pulse. So now what will happen? I'm just leaving the system on its own without any disturbance. Okay, so what will happen? Now the all the nuclei will then again experience the external external magnetic field. External magnetic field is along the plus Z axis. So they will again start experiencing the external magnetic field. So because of that, these nuclear spins, okay, the nuclear spins that got their magnetic moment, okay, oriented along the plus Y axis will again start to get back. Will start relaxing, actually, will start relaxing, and they will try to get back to their equilibrium position along and direct their nuclear spins along the external magnetic field in the plus Z axis. Okay, so what will happen? Actually, what will happen is that they will start they will start to dephase. They will start to dephase. Okay, dephase means because I have given a 90-degree pulse. Upon at the end of the 90-degree pulse, all the nuclear spins that were there, they all together got aligned along the plus Y axis. Now, since I'm giving it a relaxation time of say t, so what will happen? They will start to dephase. They won't be with each other. They won't be together with each other. After I have stopped giving the 90-degree pulse. Rather because of this chemical shift concept, what will happen? They will start to dephase. Will start to dephase because each of these nuclei will experience different type of, because they will experience different extent of external magnetic field. Okay, because of the local magnetic field. These type of concepts we have already discussed in your in week 2, in week 1, in week 3. These concepts, these basic concepts we have already discussed. The nuclei will experience, each of the nuclei, because of their different chemical environments, will experience different external magnetic fields because of each of the nuclei uh, generating a generating their own local magnetic fields. Okay, so they will start to they will start to dephase. Okay, so this is what is happening during this relaxation time of T. So they are starting to dephase. Why are they dephasing? Because each of the nuclear spins, they are getting trying to get back to the plus z axis. So if this was my this was the orientation of the magnetization, okay, at the end of the 90-degree pulse, then what is happening? Slowly and slowly, this is moving to the plus z axis. And then what we are doing, we are taking the projection of these nuclear spins in the xy plane. Okay. So if we are taking, so from here, it will go back to, it will start getting back to its equilibrium position. So if it has gone back to this equilibrium position and I'm taking the projection of it, then my projection will be this. Okay. And they are already in a precisional motion, right? So they are in a precisional motion. It is not uh, unidirectional motion. They are precessing, okay, along the uh, along the external magnetic field, and because of that, the they will start to dephase in this uh, delay of T. Now, what will happen after that? I'll be giving it a 180-degree pulse. Why is this 180? So this nomenclature is based on the RF pulse intensity, which is sufficient to cause a particular extent of uh, deviation in that magnetic field. So if it is a 180-degree pulse, that means the magnetization will get deviated by an angle of 180 degree from its initial position. If it is a 90-degree pulse, then the magnetization that is there, okay, that magnetization will get deviated from its initial position to the final position, which is at an angle, which is at an angle of 90-degree away, 90-degree deviated from the initial magnetization. Okay. Initial nuclear magnetic moment that was there. Mhm. The direction that was there. And so these are now dephasing, right? And now what I'm doing, I'm giving a 180-degree pulse. So now, so this was my bulk magnetization. Okay. Now I have applied the 90-degree pulse. So all my nuclear spins that are there, they will orient, they will get tipped up to the plus y axis. Okay, plus y axis. So all my nuclear spins are along the y axis at the end of the 90-degree pulse. Okay, and now I've stopped the 90-degree pulse. Okay, I've stopped it. So they will start to dephase. They will start to relax or dephase and get back to the original position. So they will start to dephase. And now what I'm doing, I'm applying a 180-degree pulse, 180-degree pulse. What will happen from here, from plus y, it will get shifted to minus y. Okay, from plus y, it will go in this way. Okay, this way to minus y. Okay, and now also what is happening? This has got shifted to from plus y to minus y. Okay, what will when will this happen? When I have applied this 180-degree pulse. So you have understood the figure A, right? Figure B is also clear. Okay. And after the figure B, I'm allowing it a delay time of T, right? So the nuclear spins, which of the nuclear spins are dephasing or getting relaxed. And in that time, in that duration, whatever at the end of this time T, I'm applying a 180-degree pulse. Okay, 180-degree pulse. And 180-degree pulse is applied. So what will happen from plus y axis? That magnetization will get shifted to the minus y axis. Okay, and then this at the end of the application, when I'm 180-degree at the end of the 180-degree pulse, all my nuclear spins will be uh, in the minus y axis. Okay, so it will be in the minus y x x minus y x plane. Okay, or x minus y plane. So in this plane they will be right in this plane. They will be in this plane. And now what will happen? I will again allow it a delay of time t. So during this delay, what will happen? They were getting dephased, right? They were getting dephased. So because of this time delay, and I have got the magnetization inverted from the plus y to minus y. And in the minus y plane, they are again dephasing, right? They are again dephasing because of this delay of time t. And now when they will dephase, they will not dephase like this. They will actually, because it has got inverted, they will dephase and they will come together. Okay. Because it has got inverted, they were dephasing like this. And since I have inverted, now these dephased nuclear spins, they will again refocus. They will again refocus to a single point in the y-axis. And when this refocusing of all the nuclear spins happen in that particular direction, then I will get the signal, a very strong signal. And that is the acquisition eco signal. Okay. So this is. Okay. So what happens? This pinnacle arises because of refocusing of chemical shifts. Hmm. So this is what they were dephasing, and they got what? I inverted them. So they are again coming back to their original position because of the inversion, and they will finally, what will happen? They will start coming close to each other, and at this point, all the nuclear spins have come and get together with each other, and that is where you will get this peak or the highest intensity of your signal. Hmm. So let's try to understand what I said again. So this is the spinnico or the this you are having to give some radio frequency pulse, right? So the pulse sequence, the duration for which you will give, so that you have successfully achieved this. That sequence, that pulse sequence is also known as the CPMG sequence. Why is this is called a CPMG sequence? Because it is based on the four scientists which uh, which were the contributor to behind this pulse sequence, okay, and behind this concept. So the name of those four scientists are Cart, Purcell, Meibo, and Gill. Okay, so they together gave this pulse sequence, which is known as the CPNG sequence, or because of the effect, the nuclear spin phenomena that we are seeing during the process, they are also known as spin echo experiment or spin echo sequence also it is set. Okay, so what happens in this spin echo experiment? Okay, then the spin echo experiment spins dephase due to differences in chemical shift, right? Frequency variations and inhomogeneities in the magnetic field. Okay, so I am giving a 90-degree pulse, and I am after the application of the 90-degree pulse, I'm giving it delay, right, of time t. So at that time, what happens in that time delay of time t? They are dephasing. Now, why are they dephasing? Because of two main reasons. Because of the differences in chemical shifts. This is very clear to you because of the difference in chemical environments. Each of the nuclei will show different chemical shifts or delta ppm value. Okay, or frequency variations. Okay, and that is also because one of the another reason behind the dephasing is because of inhomogeneities in the magnetic field. Okay, inhomogeneities in the magnetic field. So my external magnetic field that I'm exposing my sample to, that external magnetic field is also not homogeneous. It is inhomogeneous. Okay, you can never achieve homogeneous. Ideally, it is possible, but in the actual case, it is not possible to achieve a 100% homogeneous magnetic field. Okay, it will, it won't be homogeneous. It is always in this from not this orientation. Okay, it is curved. Right. So that will result in results in the inhomogeneity in the magnetic field. Hmm. So all my nuclear spins, they are not exposed to the same intensity of my same strength of my external magnetic field. That is what is meant by the inhomogeneity in the magnetic field. Okay. So because of these two reasons, that is inhomogeneity in the magnetic field. Okay. Inhomogeneity in the magnetic field, and because of differences in chemical shifts, my the nuclear spins, they will start dephasing, right? They will start dephasing. Now, the carboxyl Ibum Gill sequence, or the CPMG, commonly called as the CPMG sequence. Okay, sequence is commonly used to produce the sequence, the overall sequence that I explained just in the last slide. That is used to produce a spin echo and refocus, spin echo and refocus. Again, refocus these rephase spins back to back together. Okay, so what does this do? As I explained, the 90-degree RF pulse at equilibrium. First, we will allow all the nuclear magnetic spins to get back to their equilibrium position. So after the attainment of the equilibrium position, the upon the attainment of the equilibrium position, the work magnetization will be along the z-axis, right? And then what I'll do, I'll apply a 90-degree pulse. Okay. And this 90-degree pulse is 90 degree because it will is 90 degree because the bulk magnetization will get deviated by an angle of 90 degree from its initial position. So it will flip the magnetization into the XY plane, right? Into the from the Z axis, the magnetization will flip off to the XY plane. And now what will happen? I'll be giving it a delay. I will be stopping the RF pulse for some time duration, and that time duration is the delay time, or you can also call it to be the first delay, because I'll be again giving it another delay after the application of the 180-degree pulse, RF pulse. Okay, so this is therefore known as the first delay, the first delay. So during the delay time, T or tau, okay, it's actually tau, you can refer it to by this notation tau. Okay, during this delay time, spins with different precisional frequencies. Why will they be having different precisional frequencies? Because of the differences in their chemical shift or field inhomogeneities. They will start to dephase. Okay, they will start to dephase, and then they will start dephasing. Okay, they will start. The nuclear spins will start dephasing. Okay, and after the time delay, after a time delay of tau, what I'll do, I will be giving it another 180-degree RF pulse. Okay, so that radio frequency pulse will cause a deviation in the bulk magnetization by an angle of 180-degree from their initial from their initial magnetization direction from each of their nuclear magnetic spins. Okay, so after the time delay tau, 180-degree RF pulse is applied, which inverts. So this is very important. It inverts the spins actually. Because from the XY plane, get it will get inverted to X minus Y plane. Okay, this inversion reverses the phase of the spins. Okay, so it reverses the phase of the spins. So that is very, very important. This reverses, and because of the reversal of the phase, what happens? There happens refocusing of the nuclear spins. The nuclear spins refocuses. Okay, so they were dephasing like this, and then I have given it a 180-degree pulse. So while dephasing, it has uh, got deviated by 180 degree, and then they will what they will do, I will be again giving it a delay, so they will again refocus. Okay, and when they will refocus back together at a common point, then I'll get the echo or the signal will be, I'll get a magnified signal intensity at that point. Okay, and then again, because of the dephasing, I'll get a pre-induction decay. So after an additional delay time tau, the spin refocus and the echo is formed, where all spins realign and produce a coherent signal that can be detected. Okay, okay. So refocusing. So I think the concept is clear, where all spins realign and produce a coherent signal that can be detected. Coherent signal because the nuclear spins are realigning back together at a common point. Common point. Okay. And then we'll get the magnified signal. Okay. So this is the part. Okay. So they're starting to refocus, and when they refocus together at a common point, they will get this maximum signal. And then again, it will throw a pre-induction again. Okay. Because of because I have stopped the pulse. Okay. So they will again traces back to their equilibrium position. So refocusing of chemical shift, the primary purpose of the 180 pulse in a spinning sequence is to refocus the chemical shifts. Refocus the chemical shifts. When the spins are dephased, so this is the main purpose, refocus the chemical shifts. If I had not given that 180 pulse and I would have gone for the intensity measurement by just application of the 90-degree pulse, then what would have happened? I won't get that increased magnetization signal as I will be getting because of this reversal or inversion in the spin because of the 180-degree pulse. Okay, degree pulse. Because whether this be so, because of this field inhomogeneity and because of this field inhomogeneity, all of them will be not coming to the plus y-axis together. Okay, together. And also just as soon as you give the 190-degree pulse, just at the end of that 90-degree pulse, what will happen? They will just at the end of the 90-degree pulse, all of them will be together. But the duration, but it is very difficult to measure the intensity at that particular time. So when I'm giving it a delay and causing a reversal, so it will automatically come together. And at that time, my system will get the sufficient, my system recorder and detector that will be active. So it will automatically record that increased pulse upon the on the nuclear spins getting coherent. Okay. Uh, do you understand? And the spins are dephased due to the different chemical environments. The 180-degree pulse reverses this dephasing, allowing the spins to realign and produce an echo. Okay. The 180 pulse reverses this dephasing. Hmm. This dephasing, it will get reversed and they will refocus. So this refocusing is crucial for eliminating the effect of chemical shift dispersion and inhomogeneities in the magnetic field. Okay. So this is actually one of the major problems that scientists were facing in getting a very significant and very clear intensity signal in case of NMR spectroscopy. So the introduced this. They were able, they invented this kind of pulse sequence, which helped them achieve this, help them resolve the problem that they were initially facing because of the two issues of chemical shift, and that is very natural. Chemical shift you cannot avoid, and because of the inhomogeneity in the external magnetic field. Okay. I think this concept is clear. So we'll move on to the next question. So next question is, this is the question. In a spin-echo experiment, refocusing of coupling, uh, sorry, okay, refocusing of coupling evolution, okay, occurs when the spin-echo period is equal to, just what I'll do is let's shift it a bit. It's getting, this writing is getting occluded by the notification of screen sharing that I'm getting at the top. That's the problem. Okay, so in a spin-echo experiment, refocusing of coupling evolution occurs when the spin-echo period is equal to. So what are the options? The options are option A 1 by 4j, option B half j, option C 1 by j, and option D 1 by 3j. Okay, so I'll just give you a minute or two to think on the possibility of the correct option in this question. And then I'll start discussing. Okay, so let's try to understand the solution and the concept behind this question. So the answer will be 1j, 1 by j, right? Option C, 1 by j. Why? Okay, so let's try to understand this. So I think you remember the J coupling uh, concept or the scalar coupling that was discussed in week 3. Yes, it was discussed in week 3. We had a very detailed discussion in week 3. Some numericals, some co- some of the concepts related to the chemical shift and how this J coupling is related to the scalar coupling. It is a measure of what is it? I think you remember a little bit of it. If you are uh, going along with the course content, then this J coupling is a measure of how much. It is J coupling is also known as the scalar coupling constant, right? Scalar coupling constant, and it is a measure of how much the nuclear spins are separated from each other. Okay, how much the nuclear spins are separated from their adjacent nuclear spin because of the chemical environment difference. Okay, so that is the measure this J coupling. So 1j, 2j by that way because of the splitting. So how much these split peaks are separated from each other is given by the J coupling constant. Hmm. So this J coupling, also known as the scalar coupling, right? Is also known as the scalar coupling. It refers to the interaction between two nuclear spins that are connected by chemical bonds. Okay, so this splitting is seen only when when the two nuclei are connected to each other by chemical bonds. Okay, so you must have a very clear picture of this. Unlike the case where we were seeing nosy and nuclear overhauser effect or the ROE. Okay. So, Rosie, in those cases, the polarization transfer effect, it was a distance-dependent phenomena, right? It was a distance-dependent phenomena. So when the nuclei were um, separated from each other by a distance of, say, yeah, by a distance within 5 to 6 angstrom. So the distance of separation between the nuclei should be uh, less than 6 angstrom. Okay, 6 angstrom or 5 angstrom. Then you will see the you will be able to see the nuclear overhauser effect, or the polarization transfer will take place. But this J coupling is very strictly associated with nuclei. Those are those are very specifically connected to each other by chemical bonds only. Okay, the vicinity, the influence of vicinity of the nuclei spin doesn't come into picture in this case. Okay, so the strength of this interaction is measured by the J coupling constant J. It is denoted by J, right? And it is typically given in hertz. The unit is in hertz. So in an NMR experiment, what happens is coupling causes the spins of the coupled nuclei to evolve at different rates, leading to multiple splitting in the NMR spectrum. Okay, so I think you can very well understand this, whatever it is written here, because these concepts are actually based on the week 3 lecture classes and also the week 3 doubt clearing sessions that we had. Okay, so it is based on the scalar coupling concept that, okay, we had discussed in depth and in detail regarding the concept of scalar coupling. Hmm. So in an NMR experiment, this coupling causes the spins of coupled nuclei. That means the nuclei which are chemically bonded to each other, okay, to evolve at different rates. Hmm. Because of the difference in the chemical environment, leading to multiplet splitting in the NMR spectrum, right? We also solve problems and numericals on what will be the splitting, on how many peaks it will split into. Okay, we all saw that. We all discussed all those concepts also. Okay, that was based on the n+1 rule. Okay, n+1 rule, right? So that is what determines the splitting of uh, intensity, splitting of the peaks. Okay, in the frequency domain, right? The frequency domain. So, and what happens then in a spin echo and refocusing in a spin echo experiment, a 90-degree pulse is followed by a delay, right? Just what we saw in the uh, last question. We allow it a delay of time t. During this time, the magnetization of the spins starts to dephase due to both chemical shift differences and J coupling. Okay, this chemical shift difference, because of this chemical shift differences, we get to see what J coupling between the nuclei. Those are chemically bonded to each other, and 180-degree pulse is then applied. Right, Spinnaker experiment. What happens? A 180-degree pulse is applied after the delay of time t or tau. Okay, which reverses the direction of the precessing spins. Okay, it reverses the direction from the XY plane in which it was precessing. The spins got reversed to the minus YX plane, right? Causing them to refocus after an additional delay time of tau, right? Refocus, they will again refocus, and that refocus will lead to that refocusing of the nuclear spins. That is known as the echo. Okay, that is where I'll get the echo, or the maximized intensity signal, maximum peak. Hmm. What is this refocusing of coupling evolution? So the coupling evolution to be fully refocused. That is for the effects of J coupling to be refocused, the total spin echo period, right? The spin echo period, which is twice the delay time. Total time is what? T after the application of the 90-degree pulse, I'm allowing a delay of T or tau. Okay, and after the application of 180-degree pulse, I'm giving it again another delay of T or tau. Okay, so the total delay time is what? Total delay time is 2 tau. And it must match the time period associated with the J coupling, right? It must match with the time period of the J coupling. Hmm. So the coupling constant J determines the rate. Okay, so it determines the rate of oscillation of the spins due to. So this is important rate. Okay, oscillation for complete refocusing of this coupling, the echo period must match the inverse of the coupling constant. Okay, because this is the time period and J is what? J is in hertz. It is the rate. So it will be the inverse of the coupling constant J. So it is 1 by J. So the spin echo period is this is time period, and time period is equal to frequency. Okay. This is right. So in an ideal spin echo experiment designed to refocus stick coupling, the echo period T echo, say this is echo period, say T echo, that should be equal to what? 1 by J. 1 by J. The spin echo period is the total time from the initial 90-degree pulse to the point of the echo formation. Right. Starting from the 90-degree pulse. So if we go back to our previous diagram, right? This was it, right? 1 minute. Ah, so this is we are considering this time after the end of this 90-degree pulse, starting from this point to okay to their refocusing back again. Okay, so this total time is what? T plus T2T. Okay, this is also actually T or some denoted as tau also. Okay, so 2 tau. Hmm. Ah. So that is it. Okay, for additional time related. So the refocusing is sorry, there would be okay. Okay, so 2 tau. This 2 tau is actually what is denoted as the 1 by J. Okay, the spin echo period is the total time from the initial 90-degree pulse to the point of the echo formation, which includes the time for dephasing, that is tau, and the time for refocusing. This is where it is getting dephasing for time tau, and after the inverse of after applying the inverse signal by 180-degree pulse. Okay, that 180-degree pulse that will inverse by nuclear spins. Okay, that then they will refocus. Okay, so that entire time is tau plus tau, 2 tau. So this 2 tau is equal to 1 j. 1 by j is equal to 1 by j, right? Now is equal to 1 by j. So the answer to this question is, what was the question? In a spin echo experiment, refocusing of coupling evolution occurs when the spin echo period is equal to 1 by j. Okay, I think the answer is clear now. So we'll move to our next question. Okay, so this is the next question. Just move it slightly so that it does not come in the way of my notification of screen sharing. Okay, I think I'm going to go now. Okay, now it is clearly visible to me actually. So the question is, in a CH inept experiment, magnetization is transferred from proton to carbon. Which of the following operator transformation is valid in this CH inept experiment? So which operator transformation is valid? HX2, HZCY, HX2, HXCY, HX2, HZCZ, or the option D, HX2, HXCZ. Okay, so just a couple of 1 minute or two to think on this before I start explaining and trying to solve the question. Okay. So we'll try to understand a bit of this inept. Okay. What is this inept? So what is this inept? So basically, to circumvent the issues related to selective inversions, right? The inept method. The inept is also known as what? Inept is insensitive nuclei enhanced polarization transfer. Okay, which what does it do? So it what does it do? It uses these non-selective pulses for the transfer. It was developed. Okay, so there is a uh, basic pulse sequence for the inept experiment. So I think if you have gone through the classes of week 8 and week 9, then you might be knowing it just to refresh your memory. Okay, so the sequences, the pulse sequence of the inept experiment. The pulse sequence of the inept experiment goes like this, right? Ah, one minute. Ah. So, and this is what? This is 90y. Okay, this is stop. And okay, so this is the basic pulse sequence of inept experiment. Okay. Hmm. And the vector diagram, which shows the evolution of the magnetization components. How is it getting yeah, the evolution of the magnetization component happens. Remember, it is like this, right? So what I'm trying to do, that I'm trying to yeah, circumvent the issues that are related to selective inversions. Okay, because of that, I am doing this inept experiment. Huh. So this is my what? This is 180x expense and this is the 90x. Hmm. So, and this is the acquisition. Right. This is my acquisition. Okay. The acquisition. So the first, what does this do? Let's try to understand. So the first 90 x pulse. Okay. So the first 90 x pulse on the A spin. Say this is the nuclear spin. The nuclear spin that I'm going to say it is A. Okay. That nuclear spin I'm considering. The first 90x pulse on the A spin rotates the Z magnetization of the A spin onto the minus Y axis, right? So same right hand, the basic right hand thumb rule that we discussed in our first question. Okay, so 90x means this x denotes the direction of the RF pulse. Okay, the direction in which I have applied my external RF pulse. So 90x means in the x direction I have applied my RF pulse, and that RF pulse is will cause the magnetization, yeah, the bulk magnetization to tip off by an angle of 90 degree. Okay, so if I'm doing that, my extra yeah, equilibrium bulk magnetization in the along is oriented along the plus z axis, and I'm applying the RF pulse along the plus x axis. Okay, so this is if you are following the Cartesian XYZ coordination, yeah, XYZ Cartesian coordinate system, then this is my plus x, this is my plus y, and this is the z. Okay, so my bulk magnetization is along the plus z axis. I'm applying uh, RF pulse in the plus x axis, so it will cause the external magnetic bulk magnetization to tip off from the plus z to the minus y axis. Okay, so that is what will happen. That is what will happen upon application of the anti-X pulse. So at the end of this anti-X pulse, okay, interior pulse, my bulk magnetization will be oriented in the minus y axis. Hmm. So during the next tau equal to 1 by 4j period, right? Equal to 1 by 4j period, the two components dephase to the extent of 90-degree phase difference, right? And after that, what I will do, I will apply this 180-degree X pulse on the A transition, and that will cause what? It will rotate these the two transitions in the opposite quadrants, right? Because the rotation, because 180-degree X means what? It will cause inversal of the nuclear magnetic spins that were uh, initially there. Okay, that was there just at the time of the point of application of the 180-degree pulse. Okay, it rotates the two transitions in the opposite directions. A simultaneous 180-degree pulse on the X nucleus interchanges the label. So of A transition will interchange the label of A transitions, and as a result, what will happen? They will continue to dephase further, and at the end of the next 1 by 4j period, they are aligned in opposite directions along the x-axis. Okay, the following 90-degree this now. If when I'm applying this 90-degree Y pulse, following 90-degree pulse. Okay, following 90, that means after this 180-degree pulse, when I'm applying the 90-degree pulse, from the A spin, that will put these transitions along the plus Z and minus Z axis. Right. So from the same, because the yeah, right hand thumb rule, if you're following what I'm saying along with the right hand thumb rule, then this is what actually is happening. So this scenario is equivalent to a selective inversion of one of the A transitions. Describe A transitions. Okay. And that will, what will it do? It will contribute to an enhancement of the X transitions intensity by a ratio. It will enhance the intensity signals by a ratio of what? Because of this, the X transitions intensity will be enhanced by a ratio of tau A by tau X. Okay, not to do tau X. And following a 90-degree final 90-degree X pulse on the X channel, the signal is will be detected, and it will be doing a Fourier transform on the time domain signal. Okay, to get a frequency domain signal. Hmm. So the advantage of this method is what? The advantage is that the intensity enhancement by this method is much higher than that obtained by what we had earlier discussed, the NOE methods. Okay, compared to the NOE methods, the signal enhancement in this case is much higher. Okay, that is the advantage of this inept method. Hmm. So let's try and understand this. Okay, so 1 minute. Hmm. So okay, I will 1 minute. Hmm. Hmm. Okay. Now, hmm, it's so the answer is what? Answer is option A, HX2, HZCY. So what is this inept? Inept is the insensitive nuclei enhanced by polarization transport. So it is in this inept experiment also we are trying to achieve what polarization transfer only, like in case of nuclear over outer effect, Noisy and Rosy. Okay, so in those experiments like this, here also we are doing what polarization transfer only, and we are trying to enhance the sensitivity of one of the nuclei, which is not much sensitive. Okay, which is not much sensitive to the NMR recording signals, NMR spectroscopy. Okay. So the inept experiment, it is a widely used NMR technique to transfer polarization from a more sensitive nucleus, like 1H. 1H is the most sensitive nucleus because of the highest gyromagnetic ratio, to a less sensitive nucleus, like 13C. Right? Its gyromagnetic ratio is 1/4 that of the 1/4 that of the gyromagnetic ratio of proton. So it is almost 4 times less sensitive when compared to proton. So what is happening in this case? The polarization is transferred from the more sensitive nuclei like proton to the carbon. So the goal here is to enhance the signal of the less sensitive C30 nucleus by taking advantage of the higher polarization of 1H. The initial state is what? Initial state is denoted by this operator HX. It represents the magnetization along the x-axis for the proton. This is where the proton magnetization starts after an RF pulse is applied. Okay, RF pulse is applied, tipping the proton spins into the XY plane. So just at the very beginning, what are the nuclear, where in which direction are the nuclear spins oriented? In the z-axis, right? In the z-axis, all the nuclear spins are oriented. And now what I have done, I have tipped off the bulk magnetization from the plus z-axis to the XY plane. So now my bulk magnetization is along the x-axis. Okay, and this is where the proton magnetization starts after an RF pulse is applied and tipping the protons. So that is where from I will start my inept experiment. So the initial HX term, it describes the X component of the proton magnetization that is now available to be transferred. Okay, transferred to where? Transferred to the carbon atom. Okay, carbon nuclei. So after the transfer, the proton magnetization is now along the X-axis. Right. So it has, since it has transferred the polarization, so it will get back to its equilibrium position. Okay. So I'm irradiating my proton nuclei. Okay. By the application of this 90 X pulse. And that will cause what? That will cause the transfer of the polarization of the proton nuclei to the carbon nuclei. Okay. And because of this transfer, the proton nuclei will relax back to its equilibrium position, that is in the Z axis. Right. So this after the transfer, the proton region is now along the z-axis. HZ along the z-axis. So now the operator symbol that I will be using is that is HZ. And the carbon magnetization has been generated along the y-axis, CY. Okay. After this transfer, the proton magnetization, because of this transfer, it will get back to its original equilibrium position, and in turn, what will happen? It will transfer the its polarization to the carbon nuclei, and the carbon magnetization will be along the y-axis CY. Now the resulting state is HZ CY. Where HZ is what? HZ refers to resulting state is now HZ CY. Why HZ CY? Because the proton because of the transfer of its nuclei, the nuclear spin to carbon, has got back to its equilibrium state. That is HZ. And because of the transfer, the nuclear spin of carbon is in the Y, Y position. Okay. Okay. And the CY refers to the Y component of the carbon's magnetization, which has been generated through the polarization transfer. So the correct transformation is what? HX that transform the correct, it will get transformed to HZCY. In this, therefore, in the CH inert experiment, the correct transformation of the proton's magnetization during polarization transfer is from HZ. HX from HX proton X magnetization to HZCY. Proton Z magnetization coupled with carbon's Y magnetization. Okay. From proton Z magnetization coupled with carbon Y magnetization. Okay. So in summary, what we can say is that in a CH inert experiment, the correct transformation is HX to HZCY, where proton magnetization evolves from the x-axis to the z-axis. Proton magnetization, because of the transfer, it will evolve from the x-axis back to the z-axis, and the carbon magnetization is generated along the y-axis. This describes the correct transfer of polarization between two nuclei facilitated by J coupling. So the correct answer is what? HX2 is it's right. You have understood the concept. Okay. Now we'll move on to the next concept, which is as the refocused inept experiment. Okay. Do you understand? So I think you remember the class uh, in the week 8 lecture classes. So what was the case in case in this case, in a case of inept? Because we'll move on to the next concept, which is this refocused or inept plus, right? So just we'll try to understand it diagrammatically. Okay, what is happening? Hmm. Is that but the right? So this is one of the nuclei, and this is another, because this polarization transfer is taking place, right? Say this transfer is from A1 to A2. Huh. So this is what? Say this is minus y and this is say x. Okay. So allowing it a delay equal to 1 by 4j. Now what will happen? They will start to dephase. Okay. So say this is A1, this is A2, this is minus 1. They will start to dephase. Okay. And then this 180 degree cause, so it will cause the in the reversal of the nuclear spins will get inverted from here to get 180-degree shifted. So now so get exactly opposite to its initial point. Okay, initial point. So this will be what? This will be A1. This will be A2. Right. Upon the application of this, it repulsed. Okay. And then they start moving to each other. Okay. And now what I'll be doing? I'll be applying the 180 X pulse. So upon the application of this pulse, what will happen? They will start moving away from each other, right? Will start moving away from each other. A1. Okay. Because of this. Hmm. And then I will allow it a time delay of 1 by 4j. Okay. So now during this time, what will happen? Because of this time delay of equal to 1 by 4j, they will come exactly opposite to each other, A1 and A2. This is A1 spin, English planet. Okay, so now I will give what? 90-degree AY pulse. Now, so this is A1, A1 along in the plus Z axis, and this is A2. Okay, on the negative Z axis. So now again, I'll apply what? I will apply 90x. Okay. So upon the application of the 90x pulse, what will happen? They will get shifted by an angle of divided by angle x from each other. So now this will be the case, right? This will be the case. So this will be x2 and this will be x1. Okay. That's therefore now orientation will be like this. X2 because it is along the negative x. Negative x. It will be below the baseline. There is x2, and this will be the peak I'll get above the baseline. Okay. Hmm. So this is the ultimate uh, thing that you'll get. So the vector evolution of A spin magnetization components at different time points. Okay, that I showed. Hmm. So this is your first. Then it will go to here. Then third it will be here. Fourth it will be here. And finally fifth, which is this guy. Okay. So the vector evolution of spin magnetization components at different time points, 1 to 5, I have shown in this inept pulse sequence, this pulse scheme that I showed. Because of this pulse sequence, we will get this scheme. Okay. Okay. So this is it. Now we will try to understand the concept of inept plus experiment of the refocused inept experiment. Okay. So you might be knowing that the inept experiment is associated with some of the disadvantages, right? What about the disadvantages? Disadvantages are the inept experiment is associated with the multiplet anomalies. Okay, so you'll get incorrect relative intensities that occur in different spin multiplets, and this is dependent on the strength of the heteronuclear J coupling, right? And the multiplicity of the spin multiplets. Okay. So now we'll move to this inept plus or refocused inept experiment. So because of the shortcomings that we faced in the inept experiment, okay, because with regard to the multiplet distortions, and hmm, and and incorrect relative intensities. Uh, Further, what was scientists tried to develop? Scientists tried to develop the inept plus experiment or the refocused inept experiment. So what happens in this inept plus experiment? So we are trying to overcome the disadvantage of the inept experiment. So because of that, how are we trying to achieve this? The pulse sequence. Okay, that has been shown here, right? This is the pulse sequence for the refocus of the inept plus. Sure. Refocus inept experiment. Hmm. So first, what we do? First, an additional spin echo segment similar to the first one inept is added after the last 90-degree pulses. Okay, so what happens? Why is this sequence applied? Why is this done? So this helps to refocus the positive negative components. Okay. So after your in-depth experiment that you have carried out, okay, what you will do? You will apply a what will you do? You will apply a 90-degree pulse. Okay, after the last. So this helps to refocus the positive negative components that you were getting, the positive negative components. Okay, one was up, one was down. Okay, so that you will get to recover after that, the application of this from this 90-degree pulse. Okay, this modification is also known as what? This modification is actually known as referred to as the refocused synapse. And yeah, the last 90-degree pulse in the pulse sequence, it removes some artifacts and results in clean multiplex in the spectrum, right? And this final sequence is referred to as the inept plus. Final sequence. That is known as the inept plus. Okay. So this is the refocused inept experiment or the inept plus experiment. Okay. So these were the okay. This is what the signal you will get in case of each of these cases. Okay, when they're coupled, when they are decoupled. Okay, in case of inept, okay, there will be this. If they are decoupled, that means they are not coupled to each other by decoupling. Okay, or the scalar coupling. Then you will get only one peak. If they are coupled, then there will be polarization transfer, and you will get two peaks. Okay, in case of inept, because of the reversal of the nuclear spin, you will get one positive peak and another of same intensity but in the negative direction. And in case of refocus, we will be able to get a magnified intensity signal. Okay, with the comparison to the coupled component because of this pulse sequence. That is the advantage. Okay, and in case of refocus, decoupled inept, what will you get? Because they are decoupled, so you will be getting only one peak. Hmm. One peak. But because of the inept experiment, the sequence, the sequence that we discussed just now, it will result in the magnification of the initial intensity signal. So that is the advantage of this inept signal. Okay. So the sensitivity that increases because of this experiment. Hmm. So based on this concept, another question is goes like in CH refocus inept experiment, which of the following statement is correct? Right. So what are the options? Carbon and proton are decoupled during the spin eco-elements. This is the first option. The second option is carbon and proton are decoupled during the detection period. Third option is proton magnetization is detected. And the fourth option is magnetization transfer occurs from carbon to proton. Okay. Just take a couple of 1 or 2 minutes, okay, and try and see if we can solve this. Okay. I think we have tried solving the question, so we'll try to understand the correct option and the reason behind it. Right. So these were the options. Carbon and proton are decoupled during the spin equivalent elements. Carbon and proton are decoupled during the detection period. Proton magnetization is detected. And the fourth option is magnetization transfer occurs from carbon to proton. The correct option is option B. Right. Obviously. So I think if you have understood the past two concepts on INEPT and INEPT plus, along with the lecture classes, this was the recapitulation of those concepts that were discussed in week 9. So in the refocused inept variant, what happens? The sequence includes additional pulses to refocus any phase evolution that might occur due to chemical shift differences between the coupled nuclei. That is between carbon and proton. That ensures the magnetization is optimally transferred and detected. Because of this optimal transfer of the magnetization only, we are getting an increased intensity signal. Right? That was the main goal of the NF. So how it is achieved because by the addition of the extra pulse sequences to ensure the refocus of any phase evolution that might occur due to chemical shift differences between the coupled nuclei. Okay, they are coupled, but there might be some subtle chemical shift differences between the two nuclei. So this ensures that the magnetization is optimally transferred and then subsequently detected accurately. Hmm. So carbon and proton are decoupled during the spin equivalents. So in an inept experiment, carbon and proton are not decoupled during the spin equivalent. Instead, they remain coupled, right? Hmm. So instead they remain coupled, and the spin element is designed to refocus any dephasing caused by the heteronuclear scalar coupling. Heteronuclear, because here we are considering what? Proton and carbon. Proton, carbon, two different nuclei of two different elements. Okay, hydrogen and carbon. So this is caused by the heteronuclear scalar coupling. And the coupling interaction is essential during this stage for proper magnetization transfer to occur. Right. Therefore, okay. So therefore, this option A is incorrect. Right. Hmm. In the case of option B, this is the case. Option B. The option B, that is the correct. That was the correct explanation, right? Why? Because during this detection period, decoupling is applied to remove any heteronuclear J-coupling effects during the carbon and proton between the heteronuclear J-coupling between the two nuclei, that is the nuclei of the carbon and nuclei of the proton. So this allows for a cleaner, more interpretable signal by eliminating splitting caused by the J-coupling, leaving a singlet instead of a multiplet in the spectrum. So that makes analysis and work much easier because of the exclusion of the or the deletion removal of the multiplet J signal in the spectrum. Okay. So this decoupling occurs during detection to focus on the signal from one nucleus without interference from proton coupling. Right. Now, so this is right. You understood, I guess. So what is the third option? Third option was proton magnetization is detected. But what is it correct? It is not, right? Because in a CH inept experiment, what do we get? While the initial magnetization, it originates from the proton, because obviously because the protons are more sensitive, the magnetization is transferred to the carbon and the carbon magnetization is detected. Okay. So the goal of this inept is to detect the signal from the less sensitive nucleus. Okay. Less sensitive nucleus. So that's why we are doing all this uh, experiment so that the more sensitive hydrogen or the proton can transfer its polarization to carbon. So that is not the case. Therefore, this statement is incorrect, as the proton magnetization is not the one being detected in this setup, right? This is not the proton magnetization. We are detecting through this experiment, we are trying to detect the signal from a less sensitive nuclei, and that is the nuclei signal of carbon. Okay. Then uh, what is the fourth option? What was the fourth option? The fourth option was magnetization transfer. Yeah, this occurs from carbon to proton. How is this even possible? Okay, because this transfer always happens from a more sensitive and more polarized nuclei to a lesser polarized nuclei. So it is always a proton, which is more polarized because of its greater sensitivity and more gyromagnetic ratio. So the magnetization transfer happens from proton to carbon and not from, that is not possible. So this is done because these protons are more sensitive. And this polarization transfer from proton to carbon helps us in detecting the signal of the carbon. Obviously, D is for sure short wrong option, right? So this is another question. This based on the sensitivity enhancement, right? So the sensitivity enhancement in the NH refocus inept experiment is by a factor of. So these are the four options, right? A, B, C, and D. So which one is correct? 4, 10, square root 1000, or is it 8? This is the correct option. Just take a minute or two. Hmm. We've almost come to the end of today's live doubt clearing session. Okay. Try and solve it. Okay. Okay. So we will try to understand hmm, on how to solve this question. Right. So, the sensitivity of the NMR, right? It is a very less, you know that NMR is a very less sensitive technique, right? It's a very less sensitive technique because of the very uh, because we have learned because of the Boltzmann distribution. Because the lower and lower spin state and the higher spin states, they are the difference between the lower spin state and the higher spin state, that is very less. That is very less, and the population difference is also because of that is also very less. And by way of the Boltzmann distribution, because of this Boltzmann distribution, the population difference between the lower energy state and the higher energy state, higher energy spin state, they are less, making this environment a very less sensitive technique. Okay, high resolution but low sensitive. This is a problem. Okay, the sensitivity. So what does this sensitivity basically depend on? I've already studied this. One of the most critical parameters determining the sensitivity, that is the gyromagnetic ratio, right? Gyromagnetic ratio. The gyromagnetic ratio of the nuclei, okay, of the nuclei that you are all the nuclei that you are considering. So this gyromagnetic ratio is one of the key parameters that that is a key determinant determining factor of the sensitivity of the NMR along with the external magnetic field also. Okay, the higher the external magnetic field and the greater the gyromagnetic, but this gyromagnetic ratio, that is a intrinsic property of a nuclei. So you cannot actually change the gyromagnetic ratio of any. It is the inherent property of a particular nuclei. This is gamma. Okay, and also it depends on what polarization. It also depends on the polarization. Hmm. Polarization of this population difference that is there in the, and the natural abundance of the nuclear spin in each of the spin states. Okay, in each of the in the lower energy nuclear spin state and the higher nuclear spin state. Okay, so on these three things, sensitivity, the sensitivity of the NMR instrument is dependent. Hmm, that is dependent. Okay, so so in this inept experiment, the polarization transfer that occurs from a more sensitive nucleus, like we discussed. It happens from what? It happens from more sensitive nucleus, like proton. Okay, just like proton. From proton, it gets transferred to the less sensitive nucleus, say carbon or nitrogen. In case of nitrogen is even lesser sensitive. Hmm. It is like 1/10. Yeah, the additivity ratio is 1/10 that of proton. Right. So sensitivity is proportional to proportional to gamma. But the signal strength that is there, the signal strength in NMR. Okay, that signal strength is proportional to what? That we have already studied in this week 9 and week 8 actually. Week 8. That is the signal strength is proportional to this gamma cube. Okay, the cube of the diamagnetic ratio. Hmm. And obviously, this proton diamagnetic ratio, that is much higher than the diamagnetic ratio of the nitrogen. Okay, much higher. Hmm. Compared to the, like, if you remember the values, you actually can remember. It's better that you remember the values of diamagnetic ratio of at least this proton, carbon, and yeah, nitrogen. Okay. So in case of proton, the diamagnetic ratio, the gamma is value, that is approximately 26.75 into how much? 10 to the power 5, 10 to the power 7, right? Right. 26.75 into 10 to the power 7 Tesla per second. Right. While in case of nitrogen, it is what? It is almost 10 times lesser sensitive than that of than the diamagnetic than gamma H. So its value is what? Is 2.71, only 2.71. Okay. Sorry. Second. Okay. So what happens in this inept? Inept, we are this polarization transfer we are trying to achieve from the proton, which is more sensitive to the less sensitive nitrogen. Okay. This takes the advantage of the fact that this proton is, we are taking that out, and what is the enhancement in the signal because of this? Because of this, the sensitivity gets enhanced. Okay. So the sensitivity enhancement factor, that is this sensitivity gets because of the transfer of the polarization that takes place from the proton to the nitrogen. This sensitivity, there is a sensitivity enhancement, and this sensitivity enhancement is given by a factor known as sensitivity enhancement factor. And that is what? Sensitivity enhancement factor, that is approximately proportional to the square root of the diamagnetic ratio. Okay, that is the sensitivity diamagnetic ratio. Okay, of the two nuclei H. Hmm. Okay. Hmm. 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 square root of the cube of the gyromatic ratio of the more sensitive to the less sensitive. Okay. So this is the thing. So what happens? So this is 1 minute. Right. So the sense, right? The sensitivity in NMR, it depends on these factors: gyromatic ratio, polarization, and natural abundance of the nuclei involved. Okay. And this sensitivity is proportional to this gamma, and not just only the ratio of the two, but it is proportional to this cube of gamma of the more sensitive to less sensitive. So the ratio is what? The proton is 10 times more sensitive to nitrogen. Okay. So 10 cube root. So how much will it be? Equal to 1000. So the correct option is option D. Option C. Okay. This is the correct option. Okay, this is the root 1000. Okay. So next, we also in this in this week 9, you also learned the concept of the two-dimensional NMR. So, how is it different from the one-dimensional NMR? While this one-dimensional NMR, it measures the signal intensity as a function of single time domain, then transforms this data into frequency domain via Fourier transformation to generate the NMR spectrum, right? So one-dimensional because we are measuring the nuclear spin of only one nucleus. Okay, say it is only proton or it is only carbon or nitrogen. Okay, only one of the NMR uh, active nuclei, one of the NMR active nucleus is nu frequency. Okay, that we are trying to measure. And then what do we do after measuring its time domain signal? We use the Fourier transform to get a frequency domain signal. But in this two-dimensional NMR spectra, we are able to get better resolution. Okay. Some of the peaks that might have merged in the one-dimensional, we are getting better resolution because we are not only considering the nuclear spin of one of the nucleus, but in this case, we are considering the two nucleus simultaneously, say carbon or proton or nitrogen or proton. Okay, so that gives rise to two dimension. Okay, so it correlates to frequency dimensions. Example, chemical shifts of two nuclei or coupling between them. So the result is a 2D spectrum with axis representing two frequency dimensions. Okay, two frequency dimensions. So structure of a 2D NMR experiment, it consists of 4 key periods, right? So that experiment, the time, the pulse sequence. Okay, it consists of a preparation period. In this preparation period, the system is excited and prepared for coherence evolution. Then there is the actual evolution period. The magnetization evolves during a time period known as T1. Okay, during a time period T1, which is incremented in successive experiments, right? And then mixing period. Mixing period, what does it do? In this mixing period, magnetization is transferred, is allowed to transfer a mix between nuclei, often via scalar coupling or dipolar interactions. Okay, dipolar interactions, the thing uh, that gives rise to all these polarization transfer phenomena. Okay, and finally, we have the detection period, where the signal is recorded during the detection time T2. Okay, the second frequency domain is generated by systematically varying the evolution time T1. Right, so all these concepts they have already been discussed in detail in week 9. Okay, for over several iterations, we will systematically vary the evolution time, and then we'll be doing Fourier transform along with the detection time T2. Okay, into a 2D frequency spectrum. So then evolution detection or the evolution time T1 is the first time domain. that is incrementally increased across multiple scans, right? And the magnetization of the nuclei evolves according to their chemical environment. Its chemical shift couplings. Based on this, it will the magnetization of the nuclei will evolve, and this period establishes the second time variable. Right. The section time T2 is the time during which the NMR signal is directly measured. Right. Based on this concept, what is this question? This question says in a generalized two-dimensional NMR experiment, which of the following is correct? Right. So the correct option will be which one? A second time variable is generated by varying the mixing time. A second time variable is generated by varying the evolution time. Data is collected separately during evolution and detection periods. Data collected during the detection period is separated into two parts for 2D Fourier transformation. So the correct option is option B. Right. So a second time variable is generated by option option A. Sorry. Okay. The second time variable is generated by varying the mixing time. Okay. This is a correct option. Okay. So why is it so? Because the mixing time in 2D NMR is a fixed period. With this magnetization is allowed transfer between nuclei. So this is crucial in experiments such as COSY, like the correlation spectroscopy, the nuclear overhauser effect spectroscopy, or TOXI, the total correlation spectroscopy, when interactions between nuclei are detected. The second time variable in 2D NMR is not generated by varying the mixing time. Instead, what is done? It is generated by incrementally changing the evolution time T1. Therefore, this statement is incorrect. Okay. Then, okay. Okay. So the okay. So the correct option is what? Correct option is this option B. Right. Hmm. Me. And then this is wrong. Option A is this is wrong, right? And option B, the second time will be generated by varying the evolution time. This is the correct, right? In a 2D NMR experiment, the evolution time T1 is the time during which the magnetization evolves, and this is incremented across multiple scans. Each increment in T1 allows for a systematic recording of how the magnetization evolves, and Fourier transformation of this data provides the second frequency dimension. So this is the correct answer, right? Then option C, data is collected separately. No, you do not collect data separately, right? During the evolution period T1, no data is collected. The magnetization is allowed to evolve, and it is this evolution that is encoded by incrementing T1. So data is not collected during the evolution period. So this statement is actually wrong. Hmm. And this yeah, option D, data collected during the detection period is usually generated. The detection period is separated into two parts. For 2D, no. This is also not correct. The detection period T2 provides a direct observable signal, which is processed to yield one frequency domain. However, the second time variable comes from systematically varying T1. Okay, so data collected during the detection period is not responsible for generating both time variables. So this statement is also incorrect. Right. So the option which is correct is option B. Okay. So this is what brings us to the end of this week's doubt clearing session. I hope that you have understood the concepts that I discussed through the questions and some of the key concepts that were discussed in this week week 9. So I think this will help you to solve your assignment questions and also some of the doubts that you might have had in this week, in week 9. So that brings us to the end of today's session. Okay, bye.